Welcome to The Explainer. Today we're tackling one of the most famous and frankly, most misunderstood thought experiments in the entire history of science. We're going straight to the source to look at the math, the metaphor, and the really incredible physics behind the most famous feline in science, Schrödinger's cat. If you want to finally grasp how the microscopic world behaves so completely differently from our own, well, you're in the perfect place.
So, can a cat actually be dead and alive at the exact same time? I mean, if you've spent any time browsing science articles, watching sci-fi movies, or just kind of existing in pop culture, you've definitely heard of this scenario. It gets tossed around constantly as this quirky, almost magical fact of quantum physics. But is it actually true? Today, we're going to use the original 1935 thought experiment to break down exactly what's happening here, and we're going to separate the popular pop culture myth from the actual quantum mechanics.
Section 1. The famous feline paradox.
Okay, let's dive into this. When Erwin Schrödinger designed this setup back in 1935, his intent was actually to show just how absurd quantum mechanics becomes when you apply it to everyday objects. Here are the basic ingredients of his admittedly slightly morbid trap. You've got a completely sealed box containing a radioactive source, a Geiger counter, a highly fragile flask of poison, and, of course, one totally normal cat. Now, once that lid shuts, it creates a perfectly closed system. Literally zero information can get in or out.
The sheer genius of this setup is how it mechanically links the incredibly tiny, unpredictable quantum world to our normal, everyday, macroscopic world. It works like this. If that Geiger counter detects a single radioactive atom decaying, it triggers a mechanism that drops and breaks the flask of poison, and sadly, the cat dies. But if the atom doesn't decay, the flask stays perfectly intact, and the cat remains perfectly fine. So the fate of our macroscopic, everyday cat is entirely tethered to this unpredictable, microscopic quantum event. Moving on to part 2, superposition, dead and alive. To really understand why this creates such a massive paradox, we need our anchor term, superposition. According to quantum mechanics, this is a state where a particle, so in our case, the radioactive atom, literally exists in multiple states simultaneously. It is both decayed and undecayed at the exact same time. It basically hangs out in this fuzzy, undecided state until someone or something comes along to observe it. It's only upon that observation that the atom is forced to kind of snap out of it and collapse into a single definitive reality. Because the cat's life is tied directly to that specific atom state, we get this absolutely incredible conclusion. According to the rigid mathematical rules of quantum mechanics, right before we open that box to look, the cat state is basically just a linear combination of its possible outcomes. Because the atom is in a superposition of decayed and undecayed, the cat must theoretically be in a superposition of alive and dead. The entire system only collapses into one distinct state, either a living cat or a dead cat, the very second the box is opened, forcing the system into one single reality. All right, part 3, math behind the metaphor.
Let's actually lift the hood here and see how this builds, because there's a real engine driving this paradox, the time-dependent Schrödinger equation. Now, don't let the math intimidate you. In short, this equation just describes how the quantum state, which physicists often call the wave function, of a physical system changes over time. For a single non-relativistic particle, this equation dictates the absolute rules of the road. It maps out exactly how these superimposed quantum states evolve mathematically, right up until the moment an observation forces them to collapse.
Now, what's really interesting about this slide is how elegant it becomes when we de-jargon these variables. You've got psi, the wave function, which is basically just the container holding all the reachable information about our system. You combine that with the imaginary unit, Planck's constant, which scales the quantum world, and h-hat, the Hamiltonian operator representing the total kinetic and potential energy. Put all the pieces together, and the equation perfectly maps the superposition of our atom and by extension, the theoretical superposition of the entire cat state. Which brings us to part 4, quantum versus everyday reality. Let's zoom back out from the math to our macroscopic reality for a second. And this brilliantly illustrates the dramatic contrast between these two realms. In the quantum world, mathematically speaking, atoms routinely exist in multiple states at once. It's just how they work. But in our macroscopic world, the everyday reality we actually live and breathe in, we only ever observe one single reality, right? You never see a coffee cup existing on the table and off the table at the same time. You never see a cat dead and alive at the exact same time. The extreme friction between these two realms is exactly the point Schrödinger was trying to expose. So, the crucial point is that this forces a major paradigm shift. Schrödinger's cat was always intended to point out problems. It was never meant to propose a literal reality of zombie cats wandering around. It serves as this razor-sharp critique of the Copenhagen interpretation when it's just blindly applied to everyday objects. And beautifully, it highlights the deeply mysterious transition between the quantum scale and the macroscopic scale. It proves that what works flawlessly on paper for a tiny atom simply results in absolute absurdity when applied to a large cat. Which leaves us with a final, massive mystery. If the quantum world mathematically allows for superposition, but our macroscopic world strictly demands a single observable reality, where exactly is the line between the quantum world and our own? Like, at what exact point of scale, size, or complexity does a system collapse from multiple possibilities into one concrete reality? That is a fundamental question physicists are literally still debating to this day. Thank you so much for joining me on this explainer. Keep questioning the reality around you, and I'll see you next time.